Hello, my name is Kevin Davis, and this is my lab report for Lab 2, Projectile Motion. To introduce the lab, the purpose of it is to compare the position of a projectile being affected by the force of gravity experimentally using tracker and then also computationally using GlowScript, then seeing how drag, or the B value, affects the computational model. The fundamental principles of physics used in this lab include the force of gravity as a vector, which is 0, negative mg, 0. Drag force, which is the force of drag as a vector, equals negative b times the magnitude of the velocity squared times v hat, which is the direction of the velocity. Also, we use the position update formula, which states that the final position is equal to the initial position plus average velocity as a vector times the change in time. And then the velocity update formula, which is the final velocity as a vector equals the initial velocity as a vector plus the acceleration vector times the change in time. The procedure of this lab is to take a video of a projectile, in my instance a white wiffle ball, being thrown, upload it to tracker, track the point mass using the software, and then gather the experimental data. Then, using the experimental data to update the code in tracker, create a computational model of the data to see what it would look like with it being in a computational model. Then changing the drag or the B value from 0 to greater than 0 and comparing the differences between the data sets. Here is my experimental data. As you can see, each diamond is a representation of the point mass as it was falling. This is my video. And then here at the table, it shows the time values as well as the position values for both the x and the y-axis. The analysis of this data is shown here in these graphs as the position time graph of x as well as the position time graph of y. The x is upwards and constant while the y value is downwards and increasing. And then to find the initial velocity, you take the initial position, or the first position, minus the final position, or in my case the second position, divided by the changes in time for each to get the initial velocity as a vector, which is 2.3, negative 1.385 meters per second. Here is my code for the computational analysis. The m value for the mass is 21.84 grams, which converted to kilograms is as shown. The ball's position vector as well as the ball's velocity vector were calculated from the tracker analysis. Delta t is 1 divided by 30 because it represents the frame rate that we filmed it on. B is equal to 0 because for the first analysis the drag is 0. And then the force of gravity is obviously 9.8 meters per second squared. And then over here is shown the drag equation as well as the drag vector as well as the gravity vector and Fnet. Here is the computational data without drag. As you can see, the position time graph for the x value is also upwards and constant, similar to the experimental data. And then also similarly, the position time graph for the y value is downwards and increasing. And then here is the image of the computational ball that has fallen. Now, when drag is not equal to 0, or equal to 0.01 in my case, you can already see that the ball's speed of falling is decreased in its flight. The position time graph for the y appears to be downwards and constant, whereas before it was downwards and increasing, and then the position time graph for the x value is upwards and increasing at a slower rate as it continues, whereas before it was constant. These are the comparisons between the experimental data and then the computational data without drag. As you can see, they are both very similar. Now, there are some deviations, and that is because of both human error and then when filming due to camera distortion, as well as potentially when using tracker, having to do it manually, I may have tracked the point masses wrong. Additionally, outside forces and or rounding could have affected my data as well. What ifs? If the object were launched straight up with the same initial speed, would its time to reach the ground change? Explain your answer using equations or calculations. The object would stay in the air longer than the experimental trial with the same initial speed and drag equal to 0. However, if the drag were greater than 0, it would stay in the air longer, but less than with the prior scenario due to the air resistance. Do any of your models predict terminal velocity? If the answer is no, what similar experiment could you design to find the terminal velocity of your object? When drag is equal to 0, there is no terminal velocity because the velocity is constant. However, when drag is greater than 0, the answer is yes because the velocity is changing.